670 million years. That is all the time the universe had. Think about what that means. The Big Bang happened. The universe expanded and cooled. The first hydrogen and helium atoms formed. Darkness settled. Then slowly, the first threads of structure began to pull together under gravity. Gas clouds collapsed. The first stars ignited. Those first stars burned fast, lived violently, and died in catastrophic explosions. And from those deaths, the first black holes were born. That is the story we had. That was a sequence. It takes time. It has to take time. Physics demands it. 670 million years is a tight window. In cosmic terms, it is barely a prologue. The universe we live in today is nearly 14 billion years old. At 670 million years, the universe had used less than 5% of its current age. The very first generation of stars had come and gone. Most of the large-scale structures we see today were still forming. And there it was, a black hole. Not small, not quiet, not young. 1.6 billion times the mass of our sun. Already at least 1.6 billion solar masses. Already feeding. Already in a rapid accretion phase. In a universe that had barely had time to turn on its lights. Astronomers call this object J0313, 1806. We are going to call it what it is, a crime scene. Because the physics of this universe, our best equations and our most tested models, do not have a comfortable explanation for how a black hole reaches that mass in that amount of time. A black hole that size needs time to grow, more time than the universe had given it. Under standard assumptions, the math is uncomfortably tight. So something is wrong, either with the clock or with the story we told about what came first. To understand why J0313, 1806 breaks the standard story, you need to understand one law of physics and why it makes this object so difficult to explain. A quasar is what happens when a supermassive black hole feeds so aggressively that the matter swirling around it becomes hotter and brighter than anything else in the known universe. The gas falling inward releases energy at a rate that can outshine an entire galaxy of hundreds of billions of stars. Not a single star, an entire galaxy. J0313, 1806 is one of those, a feeding engine in the early universe, already in a rapid accretion phase, with an Eddington ratio measured at around 2/3 of the theoretical maximum, 1.6 billion solar masses, already in 670 million years. Here is why that number is a problem. Black holes cannot eat as fast as they like. There is a strict physical ceiling written into the laws of physics. As matter falls toward a black hole, it heats up and radiates energy outward. At a certain feeding rate, that outward radiation becomes so intense that it starts pushing back against the infalling gas. The outward pressure and the inward pull of gravity come into exact balance. This ceiling is called the Eddington Limit. The Eddington Limit is not a guideline. It is not a tendency or an average. It is a hard physical constraint that emerges directly from the balance of two fundamental forces. Every accreting black hole in the universe operates under it. Feed harder than the Eddington ceiling, and the system pushes back. The excess gas gets driven away before it can fall in. The feeding rate is self-regulating. There is no overriding it by simply wanting to grow faster. Now apply that ceiling to the growth problem. If you start with an ordinary stellar remnant seed of around 100 solar masses and feed it at the maximum rate the Eddington limit allows, the math does not close comfortably. A black hole feeding at the Eddington ceiling doubles its mass roughly every 31 million years. Run that doubling process forward from a stellar remnant seed. Do the arithmetic. You reach somewhere between 10 and 100 million solar masses in the time available. Nowhere close to 1.6 billion. The Eddington Limit is the wall, and J0313, 1806, is sitting on the wrong side of it. That leaves 3 exits from this paradox. Either the black hole started bigger than a normal stellar remnant, or it fed faster than the Eddington ceiling allows, in bursts of so-called super Eddington accretion, or the growth began far earlier than current models predict. The discovery paper worked through this arithmetic and found that even under ideal Eddington limited growth from very early cosmic times, you would need a starting seed of at least roughly 1,000 solar masses. That is a serious tension with the standard story, not a formal impossibility, but not something the old models have a comfortable answer for. J0313, 1806 was not discovered by Webb. It was announced in January 2021, before Webb had opened its eyes. But the questions it raised are exactly the questions Webb was built to answer. And since Webb began science operations, the pressure on those questions has only grown. This black hole did not merely beat the clock. It arrived like it never had to obey it. One impossible quasar is a mystery. A whole population of them is a pattern. The Hubble Space Telescope changed our picture of the universe profoundly. But Hubble works primarily in visible and ultraviolet light, and here is the problem with trying to see the early universe in visible light. The universe is expanding, and as it expands, the light traveling through it gets stretched. A photon that started its journey as ultraviolet light, emitted from a galaxy 12 or 13 billion years ago, arrives at our telescopes not as ultraviolet, but as infrared. The further back in time you look, the more extreme that red shift becomes. Hubble could not see deeply into the infrared, which meant the very earliest galaxies were effectively hidden. Webb was built to do exactly that. Its primary mirror is 6.5 meters across. More importantly, its detectors are optimized for the infrared. Webb can see what Hubble cannot. When James Webb began returning science data in 2022, astronomers started noticing something strange in the deep field images. Scattered across the early universe were thousands of small, faint reddish objects, too bright for their apparent size, too compact to match the known profiles of normal star-dominated systems, and far too common to write off as flukes. Astronomers gave them a working name: little red dots. Small, harmless sounding, easy to overlook, which is exactly what makes them suspicious. The first instinct was to treat them as ordinary galaxies reddened by cosmic expansion and dust. But when teams started getting spectroscopic data, actually breaking the light from these objects into its component wavelengths, the signatures did not look like ordinary star-forming galaxies. Spectroscopy is the key tool here. A spectrum tells you what the light is made of. Different atoms and molecules emit and absorb light at very specific wavelengths, like a fingerprint. When researchers got spectra of the little red dots, 3 things stood out. First, broad hydrogen emission lines. Under normal conditions, those emission lines are narrow. But in some little red dots, the hydrogen lines were spread wide, blurred across a range of wavelengths. That broadening is a Doppler effect. It means the gas producing those lines is moving at thousands of kilometers per second. That is not what you see in a normal galaxy. Thousands of kilometers per second is what you see when gas is orbiting very close to a black hole, where extreme gravity drives it to extreme speeds. Second, continuum shapes that did not match stellar populations. The overall energy profile of these objects did not look like the summed light of millions of stars. It matched accretion signatures, the fingerprint of gas falling into a black hole. Third, energy output that exceeded what stars alone could explain. Per unit of physical size, some of these objects were producing far more light than any known population of stars could account for. Here is one interpretation some researchers reached. Some of what we were calling galaxy light may actually be the light of gas spiraling into a black hole. Not a galaxy of stars, a black hole-dominated system wrapped in a thin veil of dust, masquerading as something far more ordinary. The dust matters here. A feeding black hole surrounded by dense dust can look very different from a naked quasar. The dust absorbs the high-energy radiation and re-emits it at longer, redder wavelengths. This is called an obscured active, galactic nucleus, a black hole that is hiding, not because it is inactive, but because its light has been processed into something harder to identify at first glance. Many of the little red dots may be exactly that. A word of caution, because this science is still live. Not every little red dot has been fully resolved. Some may be extremely dense, dusty starbursts with entirely different explanations. Some of the broad emission lines may come from dense cocoons of gas around the nucleus. Black hole mass estimates carry real uncertainty here. But here is what is not in dispute. Several little red dots have now been followed up with deeper spectroscopy, and in a number of cases, the black hole interpretation has held up under scrutiny. A NASA Webb summary from 2025 reported that a large fraction of one major sample showed signs of growing supermassive black holes. A separate study found 17 of 19 objects consistent with significant active nucleus contributions. The fraction showing convincing black hole signatures is large enough that dismissing the whole population as a misidentification is no longer a defensible position. The overall pattern is real, the numbers are large, and the fraction of them showing signs of black hole activity is too high, too consistent, and too early to explain comfortably within the old framework. The early universe is not populated by just a handful of freakishly large black holes sitting in otherwise normal galaxies. Webb suggests it may have been crowded with compact, heavily feeding, partially hidden objects that we simply could not see before. They were there the whole time. We just did not have the telescope. Webb did not find one impossible black hole. It found an entire generation hiding in plain sight. Every supermassive black hole in the universe had to begin as something smaller. The question is how small, and the answer to that question changes everything downstream. The conventional answer is light seeds. The first massive stars, called Population 3 stars, formed from pristine hydrogen and helium gas with no heavier elements. These were not stars like our Sun. Without heavy elements, these stars could not cool as efficiently as later generations. They formed at extraordinary mass, hundreds of times the mass of our Sun, possibly thousands. When those massive stars died, their collapsing cores left behind black holes of perhaps tens to a few hundred solar masses. Light seeds are clean and relatively well understood. The problem is the math. A black hole born at tens or hundreds of solar masses cannot reach 1 billion solar masses in under 700 million years, even with the most generous assumptions about feeding rates. Every interruption costs you growth, and the early universe had plenty of interruptions. So some theorists went looking for a heavier starting point. The idea is called a heavy seed, a black hole born already large. Not tens of solar masses, but tens of thousands, or even millions. If the first seeds were that big, the growth problem collapses. A black hole that starts at 100,000 solar masses and feeds at a modest fraction of the Eddington Limit can reach 1 billion solar masses in well under 1 billion years. The math works comfortably. The challenge is explaining how something that heavy forms without going through the normal stellar route. How do you build a black hole of 100,000 solar masses when normal star formation produces objects of tens of solar masses at most? The most compelling version of the heavy seed idea goes by the name of direct collapse black holes. Here is how it works. In the early universe, most regions of space contained gas clouds that were cooling, fragmenting, and breaking up into smaller and smaller clumps. Those clumps became stars. The gas cools through radiation, loses pressure support, and gravity takes over. But gravity working on a cooling cloud does not produce a single object. It produces many. The cloud fragments into thousands of smaller pieces, each one collapsing independently, each one becoming a star. But certain special regions may have been different. Imagine a cloud of pristine gas, no heavy elements, no dust, in a patch of the early universe bathed in intense radiation from nearby sources. That radiation suppresses the usual cooling mechanisms. Molecular hydrogen is one of the main cooling agents available to primordial gas. Ultraviolet radiation from nearby galaxies can dissociate molecular hydrogen, strip it apart into atoms that cool far less efficiently. Without efficient cooling, the gas cannot fragment into small pieces. The temperature stays high. The pressure stays high. The gas resists the gravitational tendency to fragment. Instead, the whole cloud, an enormous mass of gas, begins to collapse inward as a single structure. No fragmentation, no subclumping into many smaller pieces. The whole thing falls inward toward a single point. What comes out the other side is not a collection of stars. It is a single, catastrophically massive object. An object so large that it is not supported against collapse by nuclear burning the way a normal star is. It is called a supermassive star or a quasi-star, a briefly existing transitional object that is essentially a black hole forming inside a stellar envelope. The central mass crosses the threshold into a black hole almost immediately, while still accreting the surrounding gas at an enormous rate. What comes out the other side is a black hole that was never a star, a black hole that was born already large, perhaps 100,000 solar masses, perhaps more, formed in one catastrophic collapse event rather than assembled piece by piece over generations. This is a direct collapse black hole, and it would be born, in cosmic terms, almost immediately. The conditions required are rare. You need pristine gas with no heavy elements. You need an intense radiation field nearby to suppress molecular hydrogen. You need the geometry and density to be right. The window of conditions is narrow. But what makes the narrow window interesting, rather than fatal, is where it tends to occur. The best sites for direct collapse are regions near active star-forming galaxies, where the radiation environment is intense, but the target cloud is just far enough away to be illuminated rather than destroyed. These are not empty corners of the early universe. They are the busy, high-density environments where structure is already forming rapidly. A relatively small number of direct collapse events, producing massive seeds in the right places at the right times, could account for the monsters we are now finding. A black hole born at 100,000 solar masses, feeding at or near its natural limit for a few 100 million years, can reach the numbers we see in J0313, 1806, without any exotic physics. The impossible becomes merely unlikely. It is worth noting that direct collapse is not the only candidate. Some researchers point to primordial black holes formed from density fluctuations in the very first fraction of a second after the Big Bang, before any stars existed at all. Others point to the Runaway merger scenario, where massive stars in extremely dense early clusters merge with each other faster than they die, building up a single supermassive stellar core, a Nature paper on a dormant overmassive early black hole explicitly noted that current datasets still cannot cleanly differentiate between these mechanisms. The seed problem is genuinely unsolved. But direct collapse remains the leading heavy seed scenario, with strong theoretical grounding and a plausible match to the observed mass scales. These were not graves left behind by stars. They may have been foundations laid before the city existed. Here is where this stops being just a story about black holes and becomes a story about everything. We tend to think of black holes as consumers, vast, dark, passive gravity wells that wait for matter to come to them and then swallow it forever. That picture is not wrong, exactly, but it is nowhere near complete. A feeding black hole is one of the most energetically active objects in the universe. As matter spirals into the accretion disk around a black hole, enormous amounts of energy are released as radiation, heat, and outflowing gas. Some accreting black holes launch jets of material at near light speed. Many others, particularly in the compact early universe systems Webb is finding, drive powerful winds that move at thousands to tens of thousands of kilometers per second, carrying enough energy to reshape the entire gas environment of the young galaxy. This is not a passive process. This is an engine. And engines shape the environments they operate in. In a fully formed galaxy, we already know that the central black hole and the galaxy around it are somehow connected. The mass of a black hole tends to correlate with the mass of the stellar bulge surrounding it. Not loosely, tightly. A larger galaxy has a proportionally larger central black hole across a huge range of systems. That scaling relationship holds across many orders of magnitude. That is not a coincidence. It is a signal that black holes and galaxies grow together, regulating each other. The mechanism is called feedback. The black hole affects the gas in the galaxy, which affects how fast stars form, which affects how much gas falls toward the black hole. The two systems are coupled. Now push that relationship back to the very beginning. If the first heavy black hole seeds formed early, inside the densest, most gas-rich environments in the early universe, they would immediately begin feeding. The energy they released would begin pushing outward into the surrounding gas. That feedback does something paradoxical. In some regions, the outward radiation and winds strip gas away, preventing it from collapsing into stars. The black hole is suppressing star formation nearby. But in other regions, at the shells and edges of those outflows, the compression of gas by those same winds can trigger rapid star formation. Material that might have drifted without forming anything gets shoved together, hits the density threshold, and lights up. The outflow is a piston. It pushes gas at its boundaries into configurations that collapse. So the same black hole wind that destroys star formation in one zone ignites it in another. In some systems, the net effect of black hole feedback was to accelerate the assembly of the host galaxy. The black hole was building the galaxy while feeding within it. Think about what that means. The architecture of the early universe may have been shaped in part by black holes that appeared before most of the stars did, which regions became large structures, which stayed diffuse, how fast the first galaxy-scale systems assembled, all of it influenced by objects we once assumed came last. There is evidence for this in what we can already observe. Galaxies with more massive central black holes tend to have older stellar populations. Their stars formed earlier and faster, and then star formation shut down. The leading explanation is that the black hole grew large enough to drive winds that cleared the galaxy of the gas it needed to keep making stars. The black hole set a timer on the galaxy's star formation epoch. And this matters for a deeper reason than just explaining the origin of galaxies. The first galaxy seeded the formation of the next generation. The massive stars that formed in those first galaxies exploded as supernovae and scattered heavy elements, carbon, oxygen, iron, into the intergalactic medium. Those elements made the next generation of stars and planets possible. Those elements are why Earth exists. They are why you exist. If black holes helped build the first galaxies faster and more efficiently than a simple bottom-up model would predict, then they also accelerated that element seeding process. They set an earlier table for the universe that followed. We are, in a very real sense, the downstream product of things that happened in those first billion years, and the things that drove those first billion years may have had a massive black hole at their center. These objects were not simply eating the universe, they may have helped shape it. Come back to where this started. A universe 670 million years old, an object that should not exist at that age, a black hole the size of 1.6 billion suns, already burning with the light of active feeding, already shaping the gas around it, already at the center of what would become one of the earliest known quasars in the cosmos. We called it a crime scene, and it is. Something happened here that our original timeline did not predict and cannot fully explain. The detective work that followed produced a suspect. Direct collapse black holes, born already massive from pristine collapsing clouds in rare corners of the young universe. Born not from the death of stars, but from conditions that prevented stars from forming at all. That suspect has not been convicted. The case is still being built, but the evidence for something unusual, something that the standard story cannot accommodate without major revision, is now substantial enough that it cannot be argued away. And then the twist that makes the whole case stranger and more interesting than a simple origin story. These objects did not merely appear early. They fed, they radiated, they drove winds into the gas around them. They influenced which regions of the early universe concentrated into structure and which did not. Not the only builders, not even the dominant ones in most times and places, but early engines. Violent, hungry, disruptive engines that helped set the conditions for the first generations of stars, the first galaxies, the first large-scale structures that eventually, across billions of years, led to everything you can see when you look at the night sky. We think of destruction and creation as opposites. A black hole is the archetype of destruction, a singularity that consumes everything, from which nothing escapes. That is the image. That is the myth. But the universe does not respect our categories. The objects we built into symbols of pure destruction turn out to have been, in the earliest chapters of the universe's history, instruments of construction. The energy they released did not just heat gas and blow it away. It organized, it compressed, it triggered. It helped write the initial conditions from which everything else followed. This is what James Webb is doing to our picture of the cosmos, not just adding detail, not just extending what we already knew. It is revealing that some of our most fundamental assumptions about sequence and causation were wrong. The things we thought were last were, in some cases, first. The things we thought were endings were, in some cases, beginnings. Not following the story, starting it. James Webb is not done, and neither is this story. The next discovery may be even harder to explain. Watch the next video now and see what else the early cosmos is hiding from us.